Then next point, resolving power. So diffraction effects is most significant while discussing the resolving power of an optical instrument. We use an optical instrument to see minor details of all parts of an object or to see distant images of different nearby objects and not only for magnification. Now consider your friend showing two of her fingers as we do while showing a victory sign, that is V. From a distance less than 10 meter, you can easily point out that she is showing two fingers, that is, you can easily distinguish the two fingers. However, if she shows the same two fingers from a distance over 50 meter, most of you will not be able to distinguish the two fingers. That is, you can't definitely say whether those are two fingers or it is a single finger. This ability to distinguish two physically separated objects at two distinct objects is known as resolving power of an optical instrument. So, in the example given, it was your eye. In other words, from the distance less than 10 meter, your eye is able to resolve the two fingers. From beyond 50 meter, it may not possible for you to resolve two fingers. Resolving power of an optical instrument, that is an eye, a microscope, a telescope, etc., generally depends upon the aperture. So usually the diameter of lens or mirror and the wavelength of light used. In general, resolving ability of an instrument is stated in terms of visual angle, which is the angle subtended at the eye by two objects to be resolved. So, which are assumed to be point objects. It is the minimum visual angle between two objects that can be resolved by that instrument. So this minimum angle is called limit of resolution, and reciprocal of the limit of resolution is called resolving power. So Rayleigh's criterion for limit resolving, that is resolution. So for resolving power, according to Lord Rayleigh, the ability of an optical instrument to distinguish between two closely spaced objects depends upon the diffraction pattern of two objects, that is slits, point objects, stars, etc., produced at the screen. So that is retina eyepiece. According to this criterion, two objects are just resolved when the first minimum of the diffraction pattern of one source coincide with the central maximum of the diffraction pattern of the other source and vice versa. So here these are given: unresolved, just resolved, and well resolved. So in figure 17.b, first minima of the diffraction pattern of second object is coinciding with the central maximum of first and vice versa. In such a case, we find the objects to be just resolved as the diffraction in the resultant envelope is noticeable. So for figure 7.17a, the diffraction is not noticeable, and in figure 17.17c, it can be clearly noticed. So two points we will see in it. First, two linear objects. Consider two self-luminous objects, slits separated by some distance. As per Rayleigh criterion, the first minimum of diffraction pattern of one of the source should coincide with central maximum of the other. So graphical pattern of the diffraction by two slits at the just resolved condition is shown in the lower half of the figure 17.b. Okay, so you can notice here that lower half. Now, angular separation or position of first principle minimum is d theta is equal to lambda upon a. As this minimum coincides with the central maximum of the other, this must be minimum angular separation between two objects and hence the limit of resolution that instrument. So limit of resolution, that is d theta is equal to lambda upon a, and minimum separation between two linear objects that are just resolved at distance d from instrument, that is y equal to d, that is d theta is equal to d lambda upon a. It is obviously the distance of first minimum from the center. Then second, that is pair of point objects. So in the case of a microscope, quite often the objects to be viewed are similar to points object. The diffraction pattern of such objects consists of a central bright disk surrounded by a concentric rings called airy disks and rings as shown in figure 7.18. So Abbe was the first to study this thoroughly and apply it to Fraunhofer diffraction. So you can see this diagram, schematic diagram showing the formation of airy disk and ring. So, and second figure, airy disk obtained by using laser. So in figure 17.18b shows a real airy disk formed by passing a red laser beam through a 90 micrometer pinhole aperture that shows several orders or rings of diffraction. So according to Lord Rayleigh, for such objects just resolve the first ring of the diffraction pattern of first object should be formed at the center of diffraction pattern of the second, and vice versa. In other words, the minimum separation between the images of the screen is the radius of first dark ring, that is 7.17b and a. So the discussion till here is applicable to any instrument such as an eye, a microscope and a telescope, etc. And then we have to see resolving power of microscope, so which is same as nearly like a telescope, which we will see in next topic. So microscope and telescope, these are two instruments. So first of all, which we will see about microscope. So in figure 7.19 shows 2 points objects O and O dash separated by a distance a in front of an objective AB of a microscope medium between the objects, and the objective is of refractive index n. So wavelength of light emitted by the source in medium is lambda n. Angular separation between the objects at the object is 2 alpha. So that is the angle where I and I dash are centers of diffraction pattern, airy disk and rings. So due to O and O dash on the screen effectively at infinity, according to Rayleigh's criterion, the first dark ring due to O dash should coincide with I and that of O should coincide with I dash. The nature of illumination at point O on the screen is decided by A equal to 1.22 lambda. Okay, so wait student, nature of illumination at point screen is decided by the effective path difference at that point. Let us consider the point I where first dark ring due to O dash is located. Paths of extreme rays reaching I from O dash are O dash AI and O dash BI, as point I is symmetric with respect to O. So the paths AI and BI are equal, and thus the actual path difference is O dash B minus O dash A, where the region around O dash and O is highly enlarged in figure 7.19. So you can see here, okay, in figure 7.19. From this figure, it can be proved that, okay, path difference, that is dO dash plus O dash C, which is nothing but the 2a sine alpha, that is required equation. Now second, that is microscope with a pair of non-luminous objects, that is dark objects. So in common microscopy, usually self-luminous objects are not observed. Non-luminous objects are illuminated by some external source. In general, this illumination is not normal, but it is oblique. Also, majority of the objects viewed through a microscope can be considered to be point objects producing Aries ring in their diffraction pattern. Often, the eyepiece is filled with some transparent material. Let the wavelength of light in this material be lambda n is equal to lambda upon n, where lambda being the wavelength of light in air and n is the refractive index of medium. In such a setup, path difference at the first dark ring is lambda n, and from 7.30 to I alpha, sin alpha, which is equal to lambda n, which is equal to lambda upon n. So A is equal to what? Lambda upon 2n sin alpha. So lambda upon 2 into n dot A, that is numerical aperture. So factor n sin alpha is nothing but numerical aperture, and resolving power of it will be 1 upon a, which is 2 times of numerical aperture upon lambda. And microscope with self-luminous point objects is nothing but applying Abbe's theory of Airy's disks and rings to phenomena of diffraction due to a pair of self-luminous point objects. The path difference between the extreme rays at the first dark ring is given by 1.22 lambda. So for the requirement just resolution, 2a sin alpha is equal to 1.22 lambda n. So a is equal to 1.22 lambda n upon 2 sin alpha, where which is equal to 0.61 lambda upon n sin alpha, 0.61 lambda upon numerical aperture, and resolving power is nothing but what r is equal to 1 upon a, that is reciprocal, which is equal to na upon 0.61 lambda. So for better resolution, a should be minimum. This can be achieved by using an oil field objective which provides high value of n. And then next, that is the last point, resolving power of telescope. Telescopes are normally used to see distant stars for us. These stars are luminous point objects, are far off, thus their diffraction pattern as Airy disks. Also, as objects to be seen far off, only the angular separation between the two is of importance, not the linear separation between them. So in figure 7.20, okay, in this figure you can see objective AB of a telescope receiving two sets of parallel beams from two distant objects with an angular separation theta. So resolving power of a telescope is then defined as the reciprocal of least angular separation between the objects that are just resolved. So according to Rayleigh criterion, the minimum separation between the images I and I dash must be equal to the radius of first dark ring, okay, that is Airy's ring. So if Airy's theory is applied to phenomena for diffraction of a pair of a point, okay, so this point object, the path difference between the extreme rays at the first dark ring is given by 1.22 lambda, that is bi dash minus ai dash is equal to 1.22 lambda. And if d is the aperture of the telescope, so diameter of AB of its objective is bi dash minus ai dash approximately equal to d into theta, which is equal to 1.22 lambda. So therefore theta is equal to 1.22 lambda upon d, and r equal to 1 upon theta, that is which is equal to d upon 1.22 lambda. So thus to increase the resolving power of a telescope for a given wavelength, its objective aperture should be as large as possible. Using a large lens invites a lot of difficulties such as aberrations, initially molding of the lens, post launches issues such as heavy mass for changing the settings, etc. The preferred alternative is to use a front coated curved mirrors as the objective. So at discussion in 11 standard, a parabolic mirror is used in order to eliminate the spherical aberration. Again, the constructing a single large mirror invites the other difficulties. So recent telescopes are used segmented mirrors that have a number of hexagonal segments to form a large parabolic mirror. So two largest optical telescopes under the construction have 30 meter and 40 meter for the diameters of their mirrors. And radio telescope, so you can see here these are radio telescope, okay. Wavelengths of radio waves are meters according to equation 7.35. If we want to have the same limit of resolution as that of an optical telescope, the diameter, that is aperture of radio telescope, should be large, at least some kilometer. Obviously a single disc of such large diameter is impractical. In such cases, array of antenna spreads over the several kilometers are used. So GMRT, that is Giant Meter Wave Radio Telescope, located at Narangaon near Pune. So Maharashtra uses such an array consists of 30 dishes of 45 meter diameter each, spread over 25 km. It is the largest distance between two of its antenna. A photograph of GMRT dishes is shown in figure 7.21. So you can see this location when you are going from Nasik to Pune or Pune to Nasik. Okay, so in between, okay, there is a Narayangaon. Okay, so when you are traveling again, you can see these dishes, okay, from this traveling. So highest angular resolution is achievable ranges from about 60 arc second, that is arc sec is the 3600th part of the degree, at the lowest frequency of 50 megahertz to about 1 arc sec, that is at 1.4 gigahertz. Okay, so that is the information about the telescope. Okay, fine. Thank you, student.